We all know that regular, routine maintenance is essential in order to keep protection and control schemes performing as intended. However, our best efforts at testing can only be as good as the accuracy of the measuring instruments and how we use them. The objective of this videotape is to look at fundamental testing techniques and see how we can avoid some of the pitfalls that commonly occur. When we talk about electrical measurements, exactly what kind of measurement do we mean? Well, depending upon the particular circuit, we need to know the value of at least some of the following properties: voltage, AC or DC; current, AC or DC; resistance; frequency; dB signal strength; phase angle; timing. So let's first take a look at measurement of voltage. These measurements may be taken by analog-type electromagnetic meters or, in recent years, digital instruments. One of our biggest concerns has to be the accuracy of the instrument. For example, this typical analog volt-ohm meter is liable to an error as high as 3 or even 4%. However, with this analog meter, the error is less than 1%. With digital meters, the accuracy is usually within 1%, except on the very inexpensive models. Digital instruments provide better resolution. The term resolution refers to the smallest reading increment that the user can observe. When using a DMM, be aware that the accuracy of measurement may not be the same for different types of measurements. For example, with this meter, the specification indicates a DC voltage accuracy of 0.1% of the reading, plus or minus 1 digit. However, if we select this instrument to measure AC voltage, then the specified accuracy falls. The tolerance for error is now 0.6% of the reading, plus or minus 3 digits. This is for a frequency within the normal range of 45 Hertz to 2 kilohertz. Note that an error of, say, 3 digits on the scale has less significance on a full-scale reading than one at the lower end. Bear in mind when interpreting test results that the margin of error may be plus or minus. For example, this particular voltage source is known to be set at 120 volts with an accuracy of 1%. This means that the voltage may actually be anywhere within the range of 118.8 to 121.2 volts. Now suppose we're measuring this voltage with an AC digital voltmeter, which is specified as 0.75% accurate. The reading indicates 120.9 volts. One interpretation of this is that the voltage is actually 120 volts, and the voltmeter is reading 0.9 volts high, that is 0.75% of 120 volts. However, it could be that the voltmeter is actually reading 0.75% low, in which case the actual measured source voltage would be 121.8 volts, outside of its specified limits. This example shows a worst case, which is not likely to occur in practice, but it does serve to illustrate the meaning and importance of instrument accuracy. In AC circuits, the accuracy may also be affected by the characteristics of the waveform being measured. To illustrate this fact, this test circuit is used to produce a distorted secondary voltage. 2 different types of voltmeter are used. One responds to the RMS value of the voltage wave, and the other to the average value. As the primary current through the CT increases, the 2 meters indicate the same value within their respective tolerance. However, as saturation of the CT is reached, the indications differ. The readings on the 2 meters now differ by over 25%. This is because the waveform is very distorted at this point, and both instruments are calibrated for a pure sine wave. In practice, most power companies standardize on either the RMS or average type of meter only. so as to make sure all readings are compatible. Measurement errors are very likely to occur when using digital instruments in close proximity to electrical and magnetic fields. Here, we are trying to measure a small voltage across a high-resistance circuit which is located in a substation. The probability is that the nearby magnetic fields will induce a current into the meter test leads, and this in turn will produce a voltage which is superimposed upon the measured signal. Clearly, one way to reduce this error is to keep the test leads as short as possible. If you do have to use long leads, then twist them together throughout the length. In this manner, the interfering flux should be counteracted. When making voltage measurements, remember that the measured value can be affected by the impedance of the source itself. As soon as you connect the voltmeter to the circuit, additional current will flow, and this in turn will cause an additional voltage drop across the source impedance. Clearly, the higher the impedance of the voltmeter, the lower will be the additional current flow, and the more accurate will be the result. Typically, the DMM has an input impedance of 10 megohms, thus the loading effect is generally negligible. However, be aware of this problem when using an analog meter of lower impedance. It is good to remember that no circuit remains undisturbed when taking readings. When measuring currents in this live circuit, analog ammeters with less than 1% error are being used. Multimeter use is not recommended in this situation. Ensure that the accuracy level is suitable for the job. For example, when this digital multimeter is selected to measure AC current, we note that the margin of error is specified as 0.9%. This would not be adequate if we are, say, trying to adjust the output of a current transducer within a specified margin of 0.2%. The accuracy of adjustment can only be as good as that of the instrument which you are using for measurement. Consult the specifications when in doubt. Also, make sure that your multimeter is routinely calibrated. If you are measuring DC current in an inductive circuit, remember to reduce the voltage before interrupting the current flow at the end of the test. Otherwise, a large voltage may be induced into the circuit, causing damage to instruments and perhaps shock to personnel. In our activities, we are often concerned with measuring current flow in CT secondaries. The multimeter is not suitable for this job because it is fused. As you know, open-circuited CTs are a source of danger. If primary current flows, an extremely high voltage may be induced into the open-circuited secondary. For CTs and other current measurements, clamp-on current probes are most commonly used. One type of probe consists of a CT, usually wound with a convenient ratio of 1,000 to 1, so that 1 milliamp responds to 1 amp on the circuit being measured. The output can be measured by a multimeter or a millivoltmeter with a suitable shunt. For example, 200 milliamps through a 1 ohm shunt would give us a reading of 200 millivolts. Another type of current probe is the Hall effect probe. This probe actually measures the effect of DC and AC magnetic fields around conductors. In this unit, an internal energy supply is required, so you must remember to check and change the batteries periodically. Although the input signal is current, the output of the Hall effect probe is actually a voltage signal, which can be measured by a DMM. You must remember to zero the output voltage before taking the reading. In this demonstration, observe the extreme variation in reading as the instrument gets closer to the magnetic field set up by the primary current. Note that this probe is subject to significant error when used in the proximity of magnetic fields from other conductors, for example in switchgear cabinets. It is evident that a magnetic field can significantly affect the reliability of the readings. All right, let's move on now to look at measurement of resistance. Most ohm meters work on the principle of injecting a small DC current, say 1 milliamp, into the circuit under test. By measuring the voltage drop across the circuit, the resistance can be calculated and displayed. It is important that the circuit be de-energized before attempting to measure resistance. Also, when measuring the value of a resistor in a circuit, you should always lift one lead so as to avoid the possibility of parallel current paths, which will of course result in a lower resistance value. You must take special care when measuring the DC resistance of an inductive circuit, for example, a transformer winding. If the test circuit is interrupted by removing the test lead, a high voltage surge will appear across the test terminals, probably exceeding the maximum allowable input voltage. One method of protecting against this problem is to connect a diode across the winding. The preferred method of measuring resistance in an inductive circuit is by measuring volts and amps, remembering to vary the current gradually. Most ohm meters have a resolution of about 1/10 of 1 ohm, which somewhat limits their application for measuring very small resistance values. For example, in measuring the contact resistance of switchgear, special equipment must be used. We will use a low resistance tester which provides a relatively high current at a very low voltage. While speaking of resistance, we must not forget the need to measure insulation resistance. This is, of course, a very high value of resistance that is normally measured by the megger. This instrument measures DC resistance, usually in megohms. It also produces high output voltage, thus suitable precautions must always be taken. Another very useful measurement which is used to check the deterioration of insulation material is the insulation power factor test. This special test equipment measures the AC dielectric loss through the insulation. The power factor actually refers to the energy loss in watts compared to the charging current, VA. For further information on this equipment, you will have to study the manufacturer's instruction manuals. Now, at this point, it's time for all of us to take a break, and then we'll come back and continue our discussion of electrical measurements. For now, though, please switch off the tape and review this material in your workbook. Now, continuing our discussion of electrical measurements, let's take a look at frequency measurement. Most frequency counters work by measuring the number of times the waveform crosses the zero line in a specific time. Power system frequency, say 50 or 60 hertz, is fairly straightforward to measure. However, high-frequency communication channels are more difficult. We often need to measure signal strength at a specific frequency. If multiple frequencies are present in the signal, the frequency meter will not measure accurately. In this case, a spectrum analyzer may be used to examine the signal across a wide frequency range so as to detect the presence of unsuspected additional signals. When the signal frequencies are known, then a selective voltmeter can be used to check the signal strength at any selected frequency. In practice, the instrument is set up to respond to a band of frequencies either side of the selected frequency. The selective voltmeter actually filters out all other frequencies. The range of frequencies measured is known as the bandwidth. In this example, we have two signals, one at 9 kilohertz and the other at 10 kilohertz. This is the reading of the 9 kilohertz signal when a narrow bandwidth is selected. When we increase the bandwidth, the measured signal strength increases considerably due to influence from the second frequency. The bandwidth must be chosen so as to prevent energy from adjacent signals causing a measuring error. With the narrow bandwidth selected, we measure the signal strength in dBs of just the 9 kilohertz signal. On the wide bandwidth setting, we get a higher dB reading. Now hang on. What is this dB value? Well, you may remember that we talked about dB, that is decibel signals, in an earlier tape on communication systems. It is common practice to use the dB notation when measuring signal strength on communication circuits. The reason for this is that at the low values of signal strength often encountered in communication circuits, the dB scale is much more accurate to use. For example, look at these 3 voltages displayed on a linear voltage graph. You can see that it is quite difficult to accurately plot or read the very low voltage of 0.07746. Now compare this with the same voltage levels on a dB scale. Obviously, plotting the dB levels provides much greater accuracy. This is because it is in fact a logarithmic scale. The dB value is a logarithmic representation of the voltage magnitude. Let's briefly review the principle of dB measurement, which has a corresponding power level at a specified resistance value. Note that the dB scale consists of plus and minus levels. Conventionally, the 0 dB point is defined as the specific voltage which will dissipate 1 milliwatt when connected to a 600 ohm resistor. If you calculate this out, it comes to 0.7746 volts. This is RMS value, of course. The value of 600 ohms was chosen because this is approximately equal to the characteristic impedance of most telephone lines. To be precise, the value of 0.7746 volts would be written as 0 dBm bracket 600. The little m indicating 1 milliwatt, and the 600 confirming that the scale is referenced to 600 ohms. But what about other values of voltage? Well, this is related to the 0 dB equivalent voltage by the following expression. dBm bracket 600 equals 20 times log V2 divided by 0.7746. Where V2 is, say, 0.427 volts, this particular calculation comes to a value of minus 5.17 dBm bracket 600. This minus value does not mean that the voltage is negative, only that it is lower than the reference voltage. Whenever you're using dB scales or dB measuring instruments, always check the reference values, usually 600 ohm and 1 milliwatt. This is important because you may have to apply correction factors based on this information. An example of this is shown in your workbook. Many dB meters are provided with a selector switch marked bridged or terminated. The bridged selection should be used when you wish to perform dB measurements on a circuit which is already properly terminated. In the bridged position, the impedance of the meter is high, therefore having negligible effect on the circuit. However, in some cases, you may wish to measure the signal strength directly from a transmitter or signal generator with the outgoing circuit disconnected. For this purpose, the selector should be switched to the terminated position. This will now switch a 600 ohm resistor across the output to simulate the circuit impedance. Other values of resistance can be selected, say 50 or 75 ohm, depending upon the reference values required. All right, so far in this segment, we have been looking at frequency measurement and measurement of signal strength in dB. Now let's move along to look at another very important measuring instrument, that is the timer. Timing measurements can be performed by an oscilloscope, chart recorder, or digital timer. The digital timer is the most accurate, but may still give false readings if certain precautions are not taken. For example, here we have a Doble FT2 timer, which is set up to measure the dropout time of a relay. The timer will start when the relay coil is de-energized and will stop when the relay contacts open. But look, this relay operates on 125 volts DC. As we have mentioned before, when the DC current is interrupted, the magnetic field set up by the current collapses. This in turn may induce a voltage in the stop circuit, which can cause current to flow in a direction such that a premature stop signal will be produced. In fact, the timer will probably read 0. One possible solution to this problem might be to connect a diode across the coil, which slows down current decay. However, this may prolong the current flow through the coil enough to have a significant effect on the dropout time of the relay. Another possible solution is to keep the stop circuit leads as short as possible and twist them together. A better solution yet would be to install a special solid-state switch, such as the one shown here, which is not affected by magnetic induction. A description of this is included in your workbook to give you more time to study the circuit. All right, now let's turn our attention to measurement of phase angle. Correct phasing is essential for generator operation, relay directionality, and metering. Most phase angle meters work on the same principle, that is, to measure the time interval between the zero crossing of the two quantities. There are 360 degrees in one complete cycle, so the circuit is designed to convert the measured time difference into a phase angle reading. When using the instrument, great care must be taken to make sure that the circuits 1 and 2 are clearly identified, also that the polarity marks are followed. Let's look at a simple example. Here we are trying to check the phase angle difference between current and voltage, and also to check that phase rotation is correct. Our reference voltage is connected to circuit 1. As this is from the A phase, it is indicated on our phasor diagram as VA. Now, using the correct test plugs, current IA is connected to the circuit number 2 on the instrument. The phase angle is measured and shown as plus 333 degrees. So the current IA can be plotted like this on our phasor diagram. You can see that the phase angle between current and voltage is actually 27 degrees lag. Now repeat the procedure for the other two phases, current IB and IC. The results are plotted as shown here. We can see that all three phases are balanced and that phase rotation is correct. That is, IA, IB, IC in the counterclockwise direction. In order to calculate the phase angle, the instrument must very precisely measure frequency of the signals and time. Suppose in this test that the frequency was precisely 60 hertz. What would be the measured time interval between VA and IA? The time for one cycle, that is 360 degrees, will be 1 second divided by 60 equals 16.66 milliseconds. The time interval for a phase difference of 27 degrees is therefore equal to 16.66 times 27 divided by 360 equals 1.25 milliseconds. So you can see how accurate the timing measurement must be. Up to this point, we've taken a broad look at electrical measurements that are typically required in testing and calibrating protection schemes. One particularly useful measuring instrument that we have not yet discussed is the oscilloscope. We'll be looking at this in the next segment. For now, it's time for a break, so please switch off the tape and thoroughly review this material in your workbook. Occasionally, you will find that during periodic testing or troubleshooting, a picture is worth 1,000 meter measurements. The oscilloscope provides us with a graphic representation of the input signal, its waveform, frequency, amplitude, and so on. Let's first briefly review the scope's operating principles. A cathode ray tube, or CRT, contains an electron gun which produces a beam of electrons to cause the phosphor-coated face of the tube to glow. Horizontal and vertical deflection plates receive signals which make the beam move across the CRT's face. A built-in sweep generator supplies sawtooth waveforms to the horizontal deflection plates, so producing a horizontal line across the screen. The input voltage signal which we wish to observe is presented to the vertical deflection plates. The end result, a graph of time versus voltage, appears on the CRT screen. Let's take a look at the front panel controls and set up the scope for operation. This particular model is a typical two-channel non-storage scope. Let's say we turn the power switch on, but no trace appears. First, verify that the selector switch is on channel 1, as this is the channel we will be using. We look at the triggering section on the panel and observe that the auto norm control is in the norm mode. Aha! In this position, the vertical input, that is the measured signal, is used to trigger the sweep generator. But no signal has been applied yet, so we must select the auto mode. This allows the sweep generator to run free. The horizontal trace should be present now, but perhaps it is off the screen or maybe too dim to see. Adjust the horizontal position and vertical position controls to the center of their range. Increase the intensity control, if necessary, for a readable display. A word of caution on intensity, however: if the intensity is left too bright for an extended period, it will burn the CRT's phosphor coating permanently. Remember to use only enough intensity to view the display comfortably, and then turn it down when you're not using the scope for long periods. Now, the focus control can be adjusted for a clean, crisp trace. In order to apply a vertical input signal, we must connect a probe to the scope's vertical input socket. Before applying the voltage signal, check the scope and probe specifications for maximum voltage rating. Remember that the instrument is receiving a peak-to-peak voltage magnitude, which for a sine wave is 2.828 times the root mean square value. Also, check the range multiplier on the probe. Most oscilloscopes generate an internally calibrated signal source, typically a 1-volt square wave oscillating at 1 kilohertz. Connecting this known signal to the input probe allows us to observe the display and make calibration adjustments. The screen grid is marked off in centimeters. First, adjust the vertical sensitivity for 0.5 volts per centimeter. Notice that the vertical sensitivity control has an adjustable potentiometer which varies the deflection. Turn this control clockwise to the cal or calibrate position for accurate volt measurements. Now let's adjust the time division control for 0.5 milliseconds per centimeter for a measurable scale. This control can be used to change the sweep generator's frequency from seconds to nanoseconds per centimeter in order to observe a wide range of frequencies, say 1 hertz to 100 megahertz. This control also has a variable potentiometer, which must be set in the cal position for accurate time measurements. At first, the waveform may be jittery or unstable. To improve this, we can adjust the trigger level and slope, positive or negative. You will also have to place the auto norm trigger mode in the normal position now that we have an input signal. So let's see what the display is telling us. In the vertical direction, we see 2 centimeters times 0.5 volts per centimeter, which equals 1 volt. This indicates 1 volt positive with respect to chassis ground. In the horizontal direction, we see that from leading edge to leading edge, 1 cycle of the waveform covers 2 centimeters. Multiplying this by 0.5 milliseconds per centimeter equals 1 millisecond per cycle. This gives us 1,000 cycles per second, or 1 kilohertz. On some occasions, you may notice that the square wave's leading edges appear to be rounded or overshooting. To provide a clean square wave, we can vary the probe's frequency compensation adjustment. So we have now checked and adjusted the scope's accuracy and are now ready to start actual testing. Assume that a substation's solid-state equipment has been acting strangely and you are called to investigate. One possibility is that the equipment's power supply filter circuit has degraded and excessive AC ripple is interfering with the solid-state equipment's operation. You set up the scope and make the connections to look at the waveform of the DC supply. Beware, plugging the scope's three-prong power supply plug directly into a normal AC receptacle connects its chassis to ground. This also effectively grounds one side of the incoming signal. So what is the problem? Well, substation batteries and telephone circuits as well are deliberately isolated from ground. So the capacitance between the DC cables and ground cause ground to be at a potential halfway between the positive and negative feeds, say 62.5 volts DC. Now, as soon as the grounded scope chassis is connected to the equipment under test, this capacitance discharges through whatever components the reference lead is connected to and can cause catastrophic failure. This could include an unwanted trip, as well as extensive troubleshooting and repair time. On a telephone circuit, it may cause common mode voltages to be coupled to the phone line via the scope, perhaps disrupting SCADA communications or causing unexpected operation on a pilot protection scheme. Whenever making tests on solid-state or telephone equipment, be sure to use some form of isolation, such as this input isolator, so as to isolate the scope probe from ground. To continue our test then, as you decrease the volts division switch to obtain more sensitivity, the trace disappears off the top of the screen, and the vertical position control cannot bring the trace back to the screen. Aha! Here is the problem. We find this AC-DC coupling selector switch in the DC position. If we throw it to the AC position, a DC blocking capacitor is inserted in series with the input signal, so that only the AC component appears on the screen. We can now measure an AC signal in hundredths of a volt, even though it is riding on a 125-volt DC level. Of course, if we're measuring a voltage which has a ground reference, then isolation is not needed. In this example, we are testing a time delay over current ground relay. We find that the actual time current curve does not follow the manufacturer's instruction book curves. Is the test set distorting the waveform, or is the relay itself in trouble? If only we could view the current waveform to find out. Well, we can, using a Hall effect probe. You will remember that in segment A, the Hall effect clamp-on current probe was discussed for use with a digital multimeter. It turns out that this probe, because it converts a current input to a voltage output, works fine with an oscilloscope. You simply clamp it onto a current wire feeding the relay and connect its output terminals to the vertical input of the oscilloscope. As you start increasing the test current, you will see a clean sine wave at low currents. But as current increases, the wave shape starts resembling the surface of the moon. This visual proof tells you that the relay is indeed receiving distorted waveforms from the test set, and the test setup must be changed in order to achieve correct test results. The manufacturer's curves are based upon pure 60 Hertz current. Here is another practical example of the oscilloscope, testing a phase comparison relay. The manufacturer's instruction book tells you to adjust the symmetry of a squaring amplifier whose input is a 60 Hertz current signal from a line breaker's current transformers. You can obtain the waveform on the scope and adjust the appropriate potentiometer for equal on and off times of 8.33 milliseconds each. A regular multimeter could not give you the necessary picture for such a precise adjustment. The phase comparison relay also needs a propagation delay adjustment to delay the local CT signal to exactly match the CT signal from the line's remote end. Here is where a 2-channel scope enters the arena. Let us look again at the scope's vertical input section. We see a display selector switch for channel 1, channel 2, CHOP, and ALT. We have been using channel 1 only until now. Let's connect another probe to the channel 2 vertical input and select the CHOP mode. CHOP causes the 2 vertical traces to time share at a rate of about 250 kilohertz. This mode is preferred for measuring signals up to 100 kilohertz. To continue, connect the local CT signal to channel 1 and the remote CT signal to channel 2. Position the vertical position control for a convenient overlap and adjust the propagation delay pot for exact phase angle coincidence. The ALT mode is selected when measuring very high frequency signals. This causes the traces on channels 1 and 2 to alternate. At high frequencies, this is not noticeable, but it can cause an irritating flicker at lower frequencies, thus the CHOP selection. Up until now, we've been using a conventional non-storage scope. This is fine for repetitive waveforms. But at times you may need to view a one-shot occurrence, such as a digital message or trip signal which will fly by too fast. In this case, some form of image storage is required. This particular storage oscilloscope is the variable persistence type. Select the variable persistence mode on the non-storage push button to get to the storage mode. Push the erase button to remove any residual storage screen mesh charges. Select the single sweep button to prevent wipeovers. The ready light should come on, signifying the scope is armed and ready to trigger on the next vertical signal. First, make some trial runs to preset the trigger and positioning controls. Apply the input to the stage. One sweep should write across the screen. Immediately push the Save button to capture the event. You can then make observations at your leisure. In recent years, the digital storage scope has been developed. It contains a microprocessor and digital memory so that a waveform can be digitized and stored as binary data. The waveform or several waveforms can be recalled, expanded, and manipulated as necessary in order to make whatever measurements are needed. These instruments are available with liquid crystal displays and are battery-powered, so avoiding the chassis grounding problem that we get with AC-powered scopes. You have undoubtedly noticed that there are a lot more scope controls than we have discussed. However, we have attempted to cover the most commonly used controls here. But for complete mastery of your particular scope, you must study the operating instructions and practice using the controls. For now, let's take a well-deserved break. Please turn off the tape, review your workbook, and answer the self-study questions. And when you're ready, begin the next segment. When a relay is under test, we need to apply a specific value of voltage or current to simulate signals received under operating conditions. While performing the test, remember that high current or voltage can damage the relay and the test equipment if applied for a lengthy period. It has been proven that a relay's useful life is limited by accumulative thermal duty. This is mainly due to periodic testing rather than from actual power system faults. Make sure that you know the thermal rating from the instruction manual of each relay under test. Keeping these considerations firmly in mind, let's look at relay test sources. First, variable current sources. A traditional method used to measure the pickup of an overcurrent relay is to connect a variable resistor called a load box and an ammeter in series with the relay, and to feed this from the station service 115-volt AC source. The relay's output contact is monitored by an indicating light. For time over current tests, we can replace the indicating light by a timer, which is started upon relay energization and stopped by the relay's contact closure. We must be careful to begin with a very low value of current and set the ammeter on a high enough range for the expected test current. Also allow the resistance load box to cool off when necessary. This type of test set is usually limited in current output to about 30 amperes. But some relays, such as an instantaneous overcurrent relay, may require, say, 160 amps of test current. This is accomplished by using a variable inductance instead of resistance, sometimes called phantom load. A variable autotransformer known as a variac provides an adjustable input to a step-down test transformer. This in turn supplies low voltage and high current to the relay. When using this arrangement, always make sure that AC input to the variac is connected with the correct polarity. Test set manufacturers offer this type of setup in a single unit, including a contact sense light and a timer. An advantage of the phantom load is that it does not get overheated or consume energy like a resistor. However, take note that it is not suitable for testing high impedance over current relays. This is because the step-down transformer may saturate at high test currents. As a result, the time dial could be set too low, with consequent potential for misoperation. Three-phase overcurrent relays, such as pilot wire or negative sequence type, may use a test current setup like this, using variacs and ammeters. Variable three-phase voltage test sources can also be connected in a similar fashion. As always, great care must be taken to ensure that connections are correct. Let's look at this Y connection and see what would happen if we reversed the phase and ground connections to the third variac. With all wipers at their lowest position, we have just applied 120 volts to the low impedance current coil. The variac, ammeter, and the relay may have been put out of commission. Speaking of voltage sources, here is a very important testing rule. Never use bus pots, VTs, as a test source unless absolutely necessary. If station service is available, use that. Sooner or later, any one of us could accidentally create a short circuit in our test connections. Blowing a bus pot fuse can cause relay misoperation and tripping. Traditionally, a phase-shifting transformer and phase angle meter have always been used when out-of-phase voltages are required. For example, a synchro closer check relay. This setup may also be used to check the maximum torque angle of a directional overcurrent relay. This is done by shifting the phase angle of voltage with respect to the test current. Phase-shifting transformers require a three-phase input to operate. The phase angle meter's inputs are isolated from each other, so at least with this instrument, we don't have to worry about reversing ground connections and causing short circuits. However, we must observe proper test polarities so that the relay doesn't see quantities 180 degrees out of phase from what it expects. We've just been looking at the traditional type of test signal sources. You can see that a comprehensive test setup can be quite complicated and cumbersome. It may take far greater time to set up and check the test equipment than to perform the actual test. Moreover, additional special purpose test equipment is often required. For example, a test diode to produce harmonics for testing the harmonic restraint unit of a transformer differential relay. Frequency relays require a special variable frequency test set. A test resistor and reactor for plotting distance relay characteristics at several impedance angles. Over the past 20 years, this traditional type of test set has been superseded first by solid state and now by digital equipment. A solid state test set allows us to plug into a 120 volt AC single phase source and produce three-phase voltage and current quantities at any phase angle and amplitude desired.
Adjustment is by means of thumb wheel adjustments within the test set's limits. Each output source has its own on-off switch. In the 1980s, relay manufacturers began producing smart microprocessor-controlled relays which can perform many sophisticated functions beyond the reach of previous technology, such as fault location, sensing remote breaker opening without communications, oscillograph plots of recorded faults, and much, much more. Even solid-state test equipment could not exercise these relays to verify all of their functions.
As we'd expect, relay test set manufacturers rose to the occasion and began producing smart microprocessor-controlled test sets.
Most utilities are now using this type of testing. What can these units do that previous test sets cannot? Well, quite a bit, actually. Up to 6 units can be connected together, with one unit acting as the master for clock synchronization, phase angle reference, and contact sensing. 6 voltages and 6 currents can be turned on simultaneously. Back-to-back line pilot protection terminals can be tested for any type of fault. They can also be satellite synchronized for end-to-end line protection testing via computer. Where computers are used, the test sets can play back actual faults which were recorded by digital transient recorders, including high-frequency transients. New DC-coupled slave sources can even reproduce DC offsets of voltage and current waveforms. Some digital distance relays have adaptive characteristics which change their reach and angle depending upon pre-fault load parameters. Now, these characteristics can be verified. Under computer control, all output voltages and currents can be changed simultaneously from pre-fault to fault conditions. This same dynamic test capability works well for testing the fault location accuracy of digital relays. Overwhelmed? Well, don't feel lonely. The microprocessor has revolutionized protective relays and testing techniques in an amazingly short period of time. We don't have time in this tape to completely cover the digital test set, but we can look at its basic controls and capabilities. Looking at the front panel of this typical unit, we see that there are 2 test sources, 1 voltage and 1 current.
The black output terminals are grounded for protection. These light-emitting diodes, or LEDs, flash to indicate when the outputs exceed 20 volts AC.
The default source designations, VA and I1, can be changed by means of flipper switches to keep track of phases when we are doing multi-source testing. We see that both sources have phase angle and magnitude controls. The individual digits can be incremented or decremented by means of these flipper switches. All the sources which we enable by means of these switches will turn on when the single system output button is depressed. Push it again to turn off the sources. The precise point at which each output is energized depends on the setting of this selector switch. Flipping the switch to the right selects source crossing. This means that each output will turn on as its sine wave is just crossing 0 in the positive direction. This works fine for electromechanical relays where a turn-on time difference of 120 degrees is not noticeable. However, with multi-phase solid-state relays, we should select the system crossing mode. Here, the reference source, such as VA, comes on at its positive going 0 crossing. But in addition to this, the other sources, VB and VC, come on at precisely the same instant.
Test signals can be produced over a wide range of frequencies.
Pressing this flipper switch to the left changes the source's frequency from 60 Hertz all the way up to 600 Hertz in multiples of 60 Hertz. Pressing it to the right changes its source's range, 75, 150, 300 volts AC, or 3.25, 13, 26 amps AC.
Let us briefly review the requirements for test sources. Ideally, with a voltage source, the voltage level should remain fixed over the full range of output power. To achieve this, the source impedance should be low with respect to the load impedance. A current source requires that the current level remains constant over the full range of output power. So in this case, the source impedance must be high compared to the load impedance. Current relays should always be tested with a controlled current source, since the relay's impedance may change with current level. In fact, if we were to drive a non-linear relay from a voltage source, the current drawn would not be sinusoidal. However, with the current source, the high impedance of the source makes up most of the impedance in the complete circuit. This means changes in relay impedance will have little effect on the total circuit impedance, and thus for all practical purposes the current will be sinusoidal. What we're really talking about here is the regulation of the source. You will recall that the term regulation describes the amount of variation in the output from zero to full load. Percent regulation equals no load output minus full load output divided by full load output times 100. In this digital test set, both current and voltage sources are considered active, which means they have internal monitoring and self-regulation which compensates, that is, adjusts the output when the load changes. The instruction book tells us that the voltage source can deliver up to 80 volt amperes. This means that once the limit of self-regulation is reached, the source can no longer correct for errors, and the waveform and amplitude begins to stray from ideal values. The output falls rapidly, and the source will go into error.
The test set will let us know when this limit is exceeded by beeping and flashing an ER, or error message, in the source ID window. The output waveforms are continuously monitored and compared to a precision reference sine wave, which is stored as binary data in memory. The error in both magnitude and total harmonic distortion should not exceed 1%. If a voltage error does occur, we can try paralleling two voltage sources, as long as the phase angles and magnitudes are kept equal.
At times, it becomes necessary to supply more current than a single current channel can supply to a relay element, like an instantaneous overcurrent unit. In this situation, it may be possible to parallel two or several current channels. When current sources are paralleled, the currents will be added vectorially. If you need to have the magnitudes of each channel add up arithmetically, make sure that the phase angles are all equal. This practice cannot be used if the load impedance is high enough to cause an error signal. The error signal is a result of the output voltage being above the design limit. Now, back to the test set. The test set outputs can be selected by this switch to synchronize with line frequency, or to be referenced to an accurate crystal which permits variable frequency operation. When relay testing is performed in an environment where 60 Hertz magnetic fields are present, it is possible that stray induced currents may be added to the currents from the test set. When the test signals are referenced to the crystal time base, a low beat frequency may be detected in the relay response. This beat frequency is the result of the small difference between crystal and line frequencies. By switching to the line sync position, this beat phenomenon can be eliminated. However, this does not mean that the induced current has been canceled, and test results may be affected by the unwanted magnetic field interference. To verify that no appreciable error is being caused by the induced current, repeat the same test with all signals rotated by 180 degrees. We are still using line synchronization. If the results are the same, then the interference is negligible. If not, a way to reduce or eliminate the interference must be found. In any case, choosing the crystal as the usual synchronizing mode allows you to detect the presence of induced currents and take whatever action is required.
Finally, we arrive at the timer section of the panel. This reset switch resets the timer to 0 after a test. This switch, to the left, selects source 1 or source 2 as the timer start. To the right, it selects source off to on or on to off for timer start. The bottom switch selects the timer stop mode. This side panel contains connection ports to external devices such as a computer, other master units, and slave units. Slave units may include a high current source which can provide up to 160 amps at 500 VA capacity, a battery simulator, variable DC current and voltage sources, 3.25 amps and 300 volts at 62 watts.
Now, your particular test set may not be identical with the unit demonstrated, but it will certainly have similar features and controls.
We recommend that you get lots of practice in operating this equipment manually. This will enable you to become familiar with its functions and capabilities before attempting computer-controlled testing.
When you do advance to automated testing, I think you'll enjoy watching the computer push the buttons and vary the test quantities for you. Whew. At this point, we all deserve a break. Please switch off the tape now and review this material in your workbook. When we're performing tests on protection equipment, there is always the potential for personal danger because of the proximity of live circuits.
Whether you're working in the field or in the test lab, this danger can certainly be minimized if you're aware of the hazards and take the necessary precautions. Before we enter a substation or other working station, we must know precisely what our task is and the activities to be performed. We should also know what safety measures are to be carried out before commencing the work, and then what safety precautions must be adopted while performing the tests. Even before entering the locale, we must notify the system operator as to the nature of work to be performed and receive authorization to work. Never proceed without this clearance.
Ideally, you should mark up prints to indicate where isolation and grounding is required for safety, and confirm this with the system operator.
He may point out that the work area is already isolated and ready for work. You must still check this. Verify that where required, all disconnects are opened, fuses pulled, switches or valves are in the protective position, and all sources of energy are isolated. Has the equipment been adequately grounded? You should always test to ensure that the appropriate circuits are actually dead. Various approved testers are available for different voltage levels, such as hot line indicators, buzz sticks, glow detectors, multi-range voltage detectors, super testers. Always prove the tester on a live circuit before checking that your circuit is actually dead. When grounding equipment, remember to attach your grounding cable to the ground first, and then to the equipment. Generally, several grounds are attached. Remember to work between these grounds. Barricades should be placed around the work area with warning notices. This is to keep other personnel clear. All isolating points should be marked with the appropriate tags. Sample tags are indicated in your workbook. You must, of course, be completely familiar with your company clearance procedures, including tagging. Before commencing work, the test crew should review the scope of work to be performed, check prints, and identify potential hazards. For example, if a test voltage or current is to be applied, any secondary circuits and exposed connections should be isolated and tagged, as they may become energized. Also, it is good practice to remove personal items such as wristwatches, rings, keys, and so on, as they have been known to contact live circuits in delicate relay work and cause damage and perhaps injury. When performing functional testing, be sure that your test instruments are calibrated and in good working condition. Test leads must be well insulated and free of cuts and abrasions. Always use the proper tools for the job. Wear your protective gear when necessary, and above all, do not become distracted. Stay alert and keep abreast of safety procedures at all times. Good housekeeping is extremely important while performing tests. Cables, wires, and tools spread around the work area are certainly conducive to accidents. All connecting leads should be kept neat and routed out of walkways.
Remember that a relatively small accident, say tripping over a temporarily connected cable, may conceivably cause the victim to fall onto live terminals on a panel, possibly inflicting considerably more injury.
When testing relays, we would always prefer to de-energize the equipment and, if possible, remove the relay from its casing. However, we know that this is not always possible. In this situation, make the test block connections, such as external shorts and open potential circuits, before inserting the test block into the relay case. It is often necessary for us to work on live circuits. In this situation, be extremely careful to avoid contact with grounded objects. Otherwise, your body may provide a path to ground. Stand on a rubber mat if possible.
You'll remember that in an earlier videotape, we discussed at some length the hazards of working on live equipment and recommended precautions to protect equipment as well as personnel.
So far, we've been looking at very general safety precautions that apply to most work activities around the switchyard. However, there are also a number of specific hazards that very much affect the relay technician. For example, many relays include a capacitor as part of their internal circuitry. Even if the relay is de-energized, the capacitor will hold its charge for some considerable time. If you happen to place yourself across the capacitor, you'll be in for a very nasty shock. Make sure to always short the capacitor terminals before touching it. In this regard, capacitor banks can be particularly hazardous because of the high voltage and large capacity. In most installations, a discharge resistor is built into each capacitor. When the capacitor is disconnected from the power system, the resistor will discharge the unit down to, say, 50 volts within about 5 minutes. However, be aware. Experience has shown that if the resistor and capacitor are defective, it may result in the capacitor bank and also the supporting metal structure becoming energized.
Make sure that you follow your utility's safety rules when working on capacitor banks.
Another potential hazard for relay technicians involves work around potential or voltage transformers, even when disconnected. For example, when the low voltage side is energized from the test equipment, the high voltage side will provide a very high voltage across its terminals. On other occasions, you may be performing troubleshooting tests on an energized VT or PT. In this case, remember never to short circuit the secondary winding. This can prove disastrous to you as well as to the transformer. With current transformers, we have an opposite problem to the VT. We must remember to never open circuit the secondary of an energized current transformer. Very high voltage can develop across the open circuit terminals, often above 10,000 volts. Therefore, when you're measuring CT secondary current, be careful not to use any meter which contains an internal fuse. Also, make sure that the CT connection switches are all closed at the relay panel.
You should always take extreme caution when dealing with grounds.
Never disconnect a ground connection, as your body may then provide the path for ground currents. All cabinets and metallic structures in a station are normally connected to the station ground mat, so they are all ostensibly at the same ground potential. However, certain incoming cables, such as communications circuits and pilot wire circuits, may be related to ground at a remote location. Remember that this remote ground potential may be different from the local ground potential in the station. This is particularly exaggerated in the case of a line fault when ground current flows through the earth. You will remember that we discussed this matter and associated hazards in an earlier videotape in this series. The point is, you should always be wary of ground connections, particularly on incoming shielded cables. Shielding is necessary on control wiring and communications circuits to minimize interference from nearby electromagnetic and electrostatic sources. If the shield is grounded at the remote end, it may offer a high potential difference to ground in the local station.
For more information on this subject, refer to videotapes 19 and 20 in this series. A typical guide for shielding and grounding is included in your workbook. It's clear that the relay technician must always be alert to not get hurt. Always follow your company procedures when carrying out any task. If you have any doubts, consult your supervisor and make sure that you really understand the hazards of every aspect of your work. Please switch off the tape now and review this material in your workbook.